Hi guys, my name is Chris and welcome to the second video of my series Z80 with bread, in which I'm trying to build a Z80 based computer on a breadboard. Today I would like to look at address decoding and try to make an address decoder using this CPLD. So let's get started. To begin, let's talk about what address decoding actually is and why do we need it. And for that, I have prepared a simple presentation. So let's look at it. So, address decoding. What is address decoding? Address decoding is a process in which we decode the address bus and enable or disable certain chips. What do we need? We need defined address ranges for I/O and memory, and also some logic gates. But if you don't have the logic gates, you can use cheap CPLDs like ATF22V10 or ATF16V8. Today, I will be using ATF22V10. Here are the address ranges for my PC. ROM will be mapped from hex 0 to hex 7FFF. RAM will be mapped from hex 8000 to hex FFFF. And my PIO, which I would like to work with today, will be mapped from hex 8 to hex F. Here is how we are going to decode the RAM and ROM. We will be checking for A15 for switching between the RAM and ROM, and we also will be checking for memory request for it to be low. So here is a simple table. If A15 is low and memory request is low, the ROM will be enabled. And if A15 is high and memory request is low, the RAM will be enabled. Here is the simple circuit. I won't be using this circuit. I will be using the CPLD, but this is proof of concept. When you want to use the logic gates, you have an inverter and a NAND gate. The inverter inverts the memory request because the memory request will be low when the CPU wants to fetch the instruction from memory. So we are inverting it for it to be 1. And if A15 is 1, then these two inputs will be 1 and the output of a NAND gate will be 0. And here at the bottom, we have the similar circuit, but we also invert the A15. So when A15 is low and memory request is low, these two inverters invert the signal, and at the input of the NAND gate will be two ones. So 1 and 1, when they go through the NAND gate, will be 0. So this is the ROM chip select. Here is how we are going to decode the address for the PIO. We will be checking for A7 through A3. And also we are going to be checking for I/O request. I/O request is slow only when the CPU wants to output or get data from the peripheral devices, from the I/O devices. We will be using A2 for the B/A. This is the selection for the ports. The PIO has two ports, port A and port B, and we are going to be using A2 for the selection. And we are going to be using A0 for the control/data. So when A0 will be low, the data will be selected, and when A0 is high, the control will be selected. And the control and data. Control is when you want to configure the port. For example, you want to enable interrupts, or you want to switch it to input, output, or bit mask mode. And the data is for the data from the port. If you have the port in input mode, on the data line will be the data from the PIO. or if the PIO is in output, we are going to be using the data to output the data to the PIO. And we are going to be using A7 through A4 to, if they are 0, we are in our range. If you look at this table, I don't have the A7 through A6, but I only have the A5, A4, A3, A2, A1, and A0. And if you take a look, A5, A4 are 0, and A7 and A6 should be also 0. So A7, A6, A5, or A4 will be 0. A3 will be 1. And if this matches, we are in our range we want. And then I will just wire the A2 to the B/A on the PIO and A0 to the C/D on the PIO. Here is the simple circuit using logic gates. Here we invert the A5 and A4 because they are normally 0. And I don't have the A7 and A6 because I didn't want the circuit to be big and don't fit on this page. So I only have the A5, A4, and A3. So A5, A4, when they are low, this is a AND gate, and when it receives 2 1s on the inputs, the output of the AND gate will be 1. So if A5 and A4 are 0, then this output is 1, and it goes to another AND gate. And the second input of this NAND gate is A3. So when A5, A4 are 0, and A3 is 1, the output of this AND gate will be 1. And if IO request is 0, we then invert it, so it is a 1. And if this whole is 1 and IO request is 0, this output of the NAND gate will be 0. So that way we can select the PIO. And this is pretty much it for the decoding. So I will switch to some other program called CUPL, and I will be using CUPL language for the CPLD. So I will see you there. So here we are in CUPL. I've just created a simple project in which I have selected the ATF22V10C, which I have. The package I selected is 24-bit, and the option is none. I've then created the simple PLD file with this, and in that I've just added this simple header and this simple pinout. So we can start coding the CPLD. So the first thing that I'm going to do is define the input pins. So I will create a label here, input pins, close that label, and I will define pin 2 will be memory request, and don't forget to add semicolons at the end. Pin 3 will be IO request. Pin 5 will be A15. Pin 6 will be A5, A7, sorry. Pin 7 will be A6. Pin 8 will be A5. Pin 9 will be A4. And pin 10 will be A3. Now I will define the output pins. So I will create another label, output pins, the output pins, I will define pin 23 will be EEPROM chip select. Pin 22 will be RAM chip select. And pin, we'll add some new lines. Pin 21 will be PIO chip select. And now I will define the logic equations. So another label, logic equations. Close that label. And EEPROM will be low. So this bang symbol. EEPROM chip select equals memory bank memory request and A15. And this line does EEPROM chip select will be low, so this bank is a not operator. EEPROM chip select will be low when memory request is low and this ampersand is AND operation. So when memory request is low and A15 is low, the EEPROM chip select will be low. And now for the RAM will be low, the RAM chip select will be low when memory request is low and A15 is high. Now for the PIO chip select will be low when IO request is low. So we are not using the memory, we are using now the IO request. And A7 is low, and A6 is low, and A5 is low, and A4 is low, and A3 is high. And this is pretty much it for the PLD. I will close this file. Yes, save. And I will compile it. Design compiled successfully. And now I will just flash it to the CPLD and we can wire the chips up. So I've programmed the CPLD and now I will just connect it to my breadboard. So I will put it here. And I know that this pin at the bottom here, I will zoom in. This pin is the ground and this pin up here is the plus 5 volts. So I will put a jumper wire there. This is the ground. And this is the plus 5 volts. Now I will plug in the PIO. I have the Z84C20, Z80 PIO, and I will plug it somewhere over here, for example here, and I will get the datasheet for it. Here I have the datasheet. I will zoom out. Here is the datasheet, and here is the pinout. And we will go through this pinout and connect it. So the first pin that I'm going to connect is the VCC. VCC should be pin 26 on this side, and the bottom pin is 21. So 21, 22, 23, 24, 25, and 26. This should be the VCC. Now for the ground. Ground is pin 11 on this side. This is pin 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is the ground. Now for the chip enable or chip select, I'm going to take some longer wires, or maybe I will connect the chip enable later. I will now connect the data lines. So D0 of this PIO is right here, and I will connect it to the EEPROM data lines. So the EEPROM D0 is, this is the ground, this is D2, this is D2, D1, and D0. So it will be here. And I will put a shorter wire there. This is D0 and D0. Now for the D1. D1 is here on the PIO, and D1 on the EEPROM is here. Now for the D2, and the D2 on the PIO is right here, and D2 on the EEPROM is right next to the ground. Now for the D3, D3 is here, and D3 on the EEPROM is on the other side of the EEPROM. So right here. Now D4. D4 is here on the PIO next to the D3. And D4 is right next to the D3. Now for the D5. D5 is under the D4 and next to the D4 on the EEPROM. Now for the D5. D5 is right here, and D5 on the, oh sorry, D6. D6 is right here, and now for the last one, D7, and D7 is right here and in the middle of those pins. Now I will wire essential signals to the PIO from the CPU, and the first signal is the M1 or machine cycle. I will get a wire, and M1 is under D5 on the PIO, and M1 on the CPU is pin 27 next to the reset. This is the reset, and this should be the M1. Now for the IO request from the CPU. IO request is under M1 on the PIO, and IO request is on the bottom of the CPU here on this side. And
The last signal from the CPU is read, and the read signal is get a longer wire. This is the read on the PIO, and the read is on the other side of the CPU on the bottom, and this should be it. Yes. Now I will wire the chip enable and the essential signals from the CPLD. But before I do that, I will wire the CPLD up. So I will look at the pinout that I have defined. So this pin 2 on the CPLD is the memory request from the CPU. So I will connect wire to the memory request of the CPU, and the memory request is right next to the IO request on the CPU. Memory request. Now the IO request is on the CPU under memory request. This one. And IO request we have already connected to the PIO, so it is at the bottom of the CPU. Now the A15. The A15 line is right next to the clock on the CPU. I will plug it in, and this is the A15. Now for the other address lines. So this is address 7, and I will plug it to the address lines of the EEPROM. And address 7 is under address 12, and it looks like spaghetti, these wires. And this should be address 7. Under that is address 6. This will be the 6 here. Now the address 5 here on the CPLD, right next to the address 6. Address 4 here. This is address 4, and the last one is address 3, which is right here. So the CPLD is almost fully connected. Now I will just connect the chip select from the CPLD to the EEPROM. And the EEPROM chip select is right here. And the chip select on the EEPROM is right this wire. This should be connected. Now that the EEPROM has been connected, I will connect the PIO, and the PIO chip select is right here, and the chip enable on the PIO is it should be right here. Now the control/data, I will connect it to the A0. A0s should be, I will connect it to the EEPROM A0, and lastly the B/A port select, which which is right here, I will connect to A2 on the EEPROM. And I will also connect the PIO to the system clock. So here I have the big chip that generates the clock, and the clock is right next to the VCC. So here. And also I will plug a 1K resistor to the interrupt line on this PIO, which is right here, and I will pull it to VCC, to 5 volts, or maybe I can just leave it out. We'll see. Now we can program the CPU and try to output some data on the PIO. But before I do that, I will connect my LED array, zoom out, and I will connect the LEDs to A0, which is, this is address ready, B stable, A stable, and this is address 0. Now the address 1 is next, A1, A2, A3, A4, A5, A6, and I won't connect the A7 to the PIO, but I will connect it to the hold line of the CPU, so we can see if the CPU holds. Hold is here. Now I will just connect the ground, and we can start programming.
So this is where we left, and I just switched the label and I've converted the hold to lowercase. So we can start programming. First, I will define the the data and control lines on the PIO. So port A control will be at address hex 8. Port, sorry, not control data, sorry. Port A control will be at address hex 9. Port B data will be at address hex E, and port B control will be at address hex F. Now I will define the mode on the PIO, and I will be using mode 0, which is output mode. Mode 0 will be equal to hex 0F, which is only the 4 least significant bits will be 1, and you can look at the datasheet, and it states that if you want to select the mode 0, the 2 most significant bits should be 0, the next 2 we don't care, and the last 4 bits should be all ones, which is this. Now this is the start. I will remove the hold, and I will add disable interrupt. This disables the interrupts on the CPU. I will give it some time, so 2 knobs. This is just no operation. This does nothing, only takes time. You can see this is disable interrupts. Now I will create another label called PIO init in which I will add load to A. I will load the mode 0. So I will load mode 0 to A. I will load port A control to the C register, and I will output load parentheses C and A. So I will output the contents of the A register to the address at the C register. So this is just set mode 0 on the PIO. Now I will add some small delay. And now I will load to A the binary 1 0 1 0 1 0 1 0. This is just some arbitrary number that I have come up with. And now we will load to see the port A data, and we'll output it. Out C A, and this sets the output bits. And if this works, we will see the 0 1 0 1 0 1. This is A0, A1, A2, A3, A4, and so on. And we should see that on the LEDs. And I will also add a halt. So we can see the halt LED turn off. So end and halt. This should halt the CPU. I will then build it. Use this. Build it. Now we have the bin file, and I will flash it to the EEPROM, and we'll see if it works.
So the code has been flashed to the EEPROM, and we can now try to power it on. I will get this light out and turn on my lab bench and plug it in and see. Yes, here they are, the LEDs. So A0, A1, A2, A3. I'll zoom in. A0, A1, A2, A3, A4, A5, A6, and this is the halt because I didn't connect the A7. The halt works because it is slow and the halt is active low, and this is the pattern that we have selected in the code. So it looks like everything is working, and I'm really happy. And this is pretty much it for today. And in the next video, I would like to look at this SEIO, which is serial input output. And I have the FTDI adapter, and we'll take a look at this SEIO in the next video. So thank you for watching. I hope you really liked this video, and I hope you like this series, and I will see you next time. Bye.